make sure.
Okay. Also, I think that there's some people maybe knocking to come in, so just wave hello when they come in. I mean, we're going to start recording right now. Hi. Nice to meet you. I am actually starting to record for lunch right now. All right, we're going to be going over some class announcements now. So class announcements include, first of all, the quarterly. The date of the quarterly I had announced before winter break, but it is January 12th. That's 6 days from now. So you've got time to study and prepare. Hopefully you did that winter break packet over winter break to help you study and prepare. That specific winter break packet was last year's quarterly. So just to give you an idea, that's the quarterly that they actually took last year. It's not your quarterly. It was last year group's quarterly. Yes.
Isn't it going to be on units or the unit?
What did it look like in the winter break packet? I guess if you didn't do it, for anyone to know, yeah, the quarterlies, how they are in A levels, the same way they are in AS, which means that as you go through the year, there's more content on the quarterly. So you can really think of it like a midterm. It's everything that we learned from August 14 all the way to the last lesson we did. So up until the lesson I taught in before winter break. So the beginning of transition metal complexes will be on the quarterly. I will not be putting today's lesson on the quarterly to give you a little bit more time to absorb it. But the type of bell work questions that were here could definitely show up on the quarterly. So basically it's everything the first half of the year. Think of it like a midterm. Once again, that's going to be on Monday and it will take the whole class period. Expect that it will be, we'll start like not at 7:20, we'll start at 7:40, but it'll be pretty much the whole class. Yes, Ramon.
So wait, will the kind of marks be skewed in a similar way to like certain
Grade
areas?
thresholds. The Cambridge grade thresholds. I can't tell you what they are yet, but it'll be the Cambridge grade thresholds. It's usually a certain percentage that you need to hit. Yes.
I was asking more so like the topics where like some topics like appear more on test.
Whatever Cambridge chooses, I can't tell you. Usually all topics will be there. Like in the A-level class, I can tell you the A-level paper 4 doesn't really leave anything out. Unlike AS10. So expect everything can be there. Unit 1 will be there. Unit 2 will be there. Unit 3 will be there. Most topics will be there. So that's happening. Just a reminder on how that works. On the quarterlies is where you are given a level based on the amount of marks you earn, based on the Cambridge grade thresholds for that test. So I will be able to tell you the grade thresholds by next week, Monday. You'll be able to know what they are. But it's based on those grade thresholds. If you get an A level, just a reminder, that's a 120 in the grade book. That's how you know you have an A level, is I put a 120 in the grade book for quarterlies. If you have a B level on that quarterly, a 110 goes in the grade book. If you have a C level, it's a 100, a D is an 85, and an E is a 70. And the thing that's important for at least a few of you is the quarterly also replaces your lowest test grade if you do better on the quarterly than any of the 2 tests you took this quarter. So for example, if you did well on one test, but then on the other one you got like a 50%, well, as long as you pass the quarterly, a 70 would go in twice. So make sure you're studying for that, because that's coming up. The next thing is the winter packet. The winter packet is due on the day of the quarterly. The intention of that was to use the winter packet to review, to go back and study. Although the questions, it's not the same test. Like, assume that that's a good wide variety of topics to go over to get some additional practice questions. A few people were here during tutoring yesterday to go over the winter packets. That was the last tutoring before your quarterly. So just so you're aware, because your quarterly is next Monday. The next thing, and I put the winter packet, I noticed I had not put up the due date on Google. I did put it on Google Classroom, but I didn't put it as an assignment due date. I just wrote it as an announcement. So this morning I went ahead and I put the due date as an assignment for the winter packet in Google Classroom. So it's due on Monday, yes.
Could you please put the answer?
Perhaps.
I can't.
Perhaps, if I have time.
Do like, for instance, I remember reading this.
Otherwise, you can search it on, like, you can search the questions online and you can find it. That's how I do it as a teacher. Literally, you write in the first like few words of the question and you go to Google and you can find the answer. So, you can find the answers yourself. All right, so that's if I don't know what test it's coming from, like if I merged and made like a bunch of different topics from a bunch of different tests for answer keys. All right, so the next thing on the list is homework. For today's lesson, the homework for today's lesson will not be due until the 14th. And the reason why, you'll see today's lesson is going to be a little bit grainy. There's a lot of content in this lesson today. So we're going to try to get through everything that's in the packet. And if we don't get through everything, I still have like built in Thursday as well for this same topic. The goal, the stretch goal would be to get through everything today and then just do activities and review on Thursday. But whatever we don't do in today's lesson, we have to finish on Thursday. So goal is to finish, this is what I taught for lesson 5 last year. And then next class will be a lab. So make sure that you are not wearing props that day, that you have it in your schedule to be in proper lab attire. Because the second part of the topic today is going to be something that you'll much better learn with a lab. So last thing on the list that I had for announcements is the Olympiad. So the American Chemical Society Olympiad, some of you did this competition last year, bless you. If you are potentially going to do that competition, you need to register through the American Chemical Society. There is a link. So you need to register and your parents need to register you. It's free. The competition is free. The goal is I have it to be on March 2nd after school. So March 2nd is the anticipated date of it. Once again, if you are going to be registering for that competition, you need to do it by next week, Friday. Next week, Friday is the official deadline. Next week, Thursday is the last day of like school we have because there's no school next Friday. So I won't be able to remind you on Friday to do it. So once again, that's for those of you that are interested in doing the American Chemical Society Olympiad. If you have not yet registered, I posted it all the way back in October with the information. I just reposted it as an assignment now. Make sure that you sign up if you're interested and that you also message me and let me know that you did so that I can anticipate how many students will be doing the competition. This is this competition with the practice sets I've been posting as extra credit for the class. And just so you're aware, if you do the competition, that will actually be another extra credit itself for this class. So you'll get a little extra credit bonus for quarter 3, which is all organic chemistry, if you're doing the Olympiad. Yes. All right, so I think that's all the announcements I had. So now I'm going to go ahead and get started with today's lesson. All right, so here's our objectives. It looks like a not scary amount of objectives. There's 4. Let's take a look at what it says. And actually, the first one we already did, but I figured you might have forgotten, so I'm just going to go back over it quickly. Describe the geometry, which is the shape and bond angle, of transition element complexes which are linear. They specifically want you to know linear, square planar, tetrahedral, and octahedral. And then explain qualitatively that ligand exchange can occur, including the complexes of copper 2 ions and cobalt 2 ions with water and ammonia molecules, hydroxide and fluoride ions. This standard is hefty because not only do you have to do a ligand exchange equations for this, you will also have to describe the colors of every potential complex. Meaning you will have to know the color of copper with water. You'll have to know the color of copper with ammonia, copper hydroxide, and copper with chlorine. And that's where the lab next class is going to come into play because you're actually going to do the reactions and see it. So you'll have reference for it. But this is a much heftier standard than what it seems like. And then I copy pasted the stereoisomerism ones. They're down here. Describe the types of stereoisomerism shown by transition complexes, including those with bidentate ligands. And so you're going to have to know cis-trans isomerism for square planar molecules and for octahedral molecules. And the examples they give is when you have 6 ligands, 4 of one type, 2 of another. And then here, this is 2 bidentate ligands and 2 monodentate ligands. And so you'll have to describe their geometry and when they make cis-trans, and also if they make optical isomers. So I have a video for it that I like to show that I think is helpful because it is really big, complex molecules. And then the final objective here is deduce the polarity of these complexes. So you're going to have to be able to tell which isomer is polar, the cis one or the trans one. So with that being said, let's get to business. It's a pretty long lesson, like I said. This is where we start. Molecular geometry. This was actually on our lesson 4 slides. You do have to know by heart the bond angles for each of these. It was in your homework. What was octahedral again?
8.
The bond angle? 90. And tetrahedral? 109.5. Linear? 180. And square planar, which is here. What's square planar? 90. And so you do have to have the bond angles and the shapes of the different complexes down by heart. For hybridization, I included that here, but Cambridge really only asks hybridization up through tetrahedral. They do not ask hybridization for square planar or trigonal bipyramidal or octahedral, but I did include it for upgrade. This is also a review of what we did before in a way, because we're just talking about how complexes form. Here, this is showing what happens when copper goes into water. When copper goes into water, you actually have what we used to call CuAq, Cu2 plus AQ. Now you need to know as CuH2O6, 2 plus, because that's copper in water. 6 water molecules bind to the copper in the middle. So it's like this, copper 2 plus, and then you've got a water, and then water. Why am I writing the O's the way that I am? Because the oxygens would have the unshared pair, and when you show the bonding, you have to show the bonding connecting to the oxygen, not the hydrogen. And so you have to be careful with that for Cambridge. So this is actually copper that's in water, copper water aqueous. And then this is cobalt with NH3. It makes this complex. That's just a review of what we had done before, how that occurs. Here's where we start. So stereoisomers is where we're going to start. For geometric isomerism, you have to remember that there's 2 types. One is called cis and the other one is called trans. In AS chemistry, we did isomerism around a double bond, where I had taught you, you could remember cis was the same side, and then trans would be the opposite side. But here, there is no double bond in a square planar complex. So how would you know if you had cis or trans? Take a look at these two. They tell you that this one is cis, this one is trans. How do you know which one's cis or trans? Like, what's the same side now? If your 2 atoms are next to each other, it's cis. And if they're across from each other, it's trans. So 2 atoms next to each other or groups is cis, and the groups are across from each other. that's trans. And so I have a square planar, or I have the cis and trans square planars to show you here, just with a little model kit. If we have the time on Thursday, I'd like to break them out. However, in order to build the stuff that I built over there, it took me 2 model kits. So I have to look at how much I have for the size of our class. But this is the cis one. This is the trans. So my question is, can you deduce the polarity? Which one would be polar? Which one would be non-polar? Isa. Cis is polar. And you should write that down. The cis is polar, and that's because you have 2 groups pulling in the same direction, and then the other 2 groups are pulling in the same direction with an opposite amount of force. And so these have a different power than these do. So this would be a polar molecule. And the trans would be non-polar. Why? It's symmetric, and the groups are pulling 180 degrees apart with the same exact amount of power as each other. So the trans is going to be non-polar. And Cambridge did say they wanted to deduce polarity. So that's how you would deduce polarity for the square planar. On the next slide, this next topic is no longer a required standard from Cambridge, but I think it's interesting, so I left the slide in. And there's a non-zero chance they can still give you this molecule to look at, but they used to have more information about this. It's a biochemistry, well, it really has to do with medicine. Because when we talk about chemotherapy for cancer treatment, the actual main chemotherapy drug that's been used is cisplatin. Cisplatin is this. So this is used in chemotherapy. And it actually matters whether you have cisplatin or transplatin. And I think you may remember from AS chemistry, I had mentioned that the isomers, one would work in a medicine and the other one would not work based on the isomerism. So cisplatin, that's used as a drug for chemotherapy, and it binds the sections of the DNA in cancer cells, which prevents cell division. It basically binds to them, so it will cause cell death. The problem is it doesn't just target cancer cells. It also targets all cells. So that's why people who undergo chemotherapy, they do get sick from it, because it targets both your cancer cells and your regular cells. It's not as selective as some of the other methods people are, coming up with. And so transplatin is actually ineffective. It is toxic. And so you have to make sure if you're developing the medication for chemotherapy that you're only getting the cis version and not the trans version. So there are ways to do that. One of our last topics of the actual school year is how to, it's in the organic chemistry segment, is how to ensure you get one variant of an isomer and not the other. Actually, that's one of the very last topics in organic chemistry, in the organic chemistry section of the class. But I just wanted to show you, this is an example of a square planar where the cis version is effective and the trans version is not effective. All right, so this is the type of question you see on paper 4. Complex NiBr2CN2 2- shows stereoisomerism. Draw diagrams to show the 2 isomers. So for square planar, what I always do is I will always think of it like octahedral, but just leave out the top part and the bottom part. So just the dashes and the wedges. And then here, this is, again,
Do you need to show like which the extra atoms?
yeah. This is just me setting it up. I don't have a single mark right now. So this is just me preparing it. So now I have to plug in my bromines and my cyanides. For my one variant, it doesn't matter. They're not saying which one has to be the cis, which one has to be the trans. So you just pick how you want to do it. How do you want to place your bromines for isomer 1 on the left?
Next to each other.
Next to each other on the top? Okay. Which means that the CNs have to be on the bottom. So then how would we switch it for isomer 2? What? Like what would be across?
The other one color with the other one.
Correct. So this would be the second isomer. And then CN would go like this, and the CN would go like this.
You don't just do a line, do you have to do the,
You can do it with the 4, like with the lines with 4, you can, and then just put them next to each other or across from each other. I just like to keep it like this because it's very similar to the octahedral, except without the top and bottom. But yes, that's doable. This is worth 1 point. What I've written is worth 1 point. The second point is to state what is the type of stereoisomerism. What is it? Geometric. Geometric, but they also accept this trans.
Will they always accept cis trans?
From every mark scheme I've seen, yeah. I've never seen them say reject cis trans. But it's technically geometric isomerism. All right, so square planar only does cis trans isomerism when you have 2 of each group. Make sure you fill in the bottom part. I'm about to move forward. So try one yourself. Very similar. But this time I want you to label cis and the trans isomer. Also, identify which is polar and which is non-polar. So try this one yourself. That's not cis.
Look, the wedges.
So-
It doesn't matter. It's like they're
It's to show, well, the way that you have it
yeah, it's
is like, because you have it, I guess, like this. You have it like this. This is what you have. It's still not cis. These bromines are 180 degrees apart from each other. Like, look, the CN here and the CN there are 180 degrees apart from each other.
this is like this is coming downwards.
Are you sure? Like, you weren't like looking to like.
It's like
Well, why do you have them like written like this or the wedges like that?
I know I'm gonna stop.
Right here.
Oh, this could be cis. Yeah. Yeah.
Like the wedges.
I think, yeah, it does.
You sure you
Yeah,
I would try not to overcomplicate it because it's going to get overcomplicated really quickly.
yeah, I know what I'm doing.
Okay, good.
Wait.
Back here.
I think it's just what it's
No, I know what I'm doing.
I would just keep it the general format. Try not to overcomplicate it. Yeah.
It's not.
No, you wait. If it's,
Good job.
In your backpack.
this is.
Good job.
Is it?
All right. Anybody else see to check?
Okay.
You're there.
Now is it?
Yes, Ramon.
Okay, good.
Yes.
Sure this spot. Yeah, they just do it, but they 2 plus 3 degrees. But they're open, but then that's when it's different series. Well, we
double?
have our probability and suited for AC.
Good job. Wait. There's probably polarity drops. Polar? You think polar, which one's non-polar?
Oh.
Yeah. Well, I mean, I would. If you're doing it without the red,
Yeah.
What?
That would be the cis. And without it. That's what you, that's.
It's just. I have a question. It's just more precise. You do it like this and it would still be like. Like, does it matter if you put it at the top or open at the sides?
They just have to be next to each other.
Okay.
like this. All right, so this was type 1, variant 1, which is cis trans isomerism in square planar molecules. And so variant 2 is cis-trans isomerism in octahedral molecules. Now, before I show you this, I think, let me check.
We'll just pull it out for
I do have a video. I think I'll show it to you now, though. This to you now, and then I'll get to the video. So cis-trans isomerism in octahedral.
Why is this case?
The easiest way to remember how to do this, first of all, is to remember that trans is still opposite and cis means same, right? So if trans means opposite and cis means the same, the idea here is whatever you have only two of, for the cis, you're going to want to put them next to each other,
Yeah.
and for the trans, you're going to want to put them apart. So looking at this molecule, you've got 2 CH3NH2s and 4 waters. So I'm going to show you the way that I would envision how to do this the easiest. First, fill in your, they've partially filled this in for you, but not completely filled it in. So fill in your wedges and your dashes. If you do your wedges and your dashes a different way, like a few of you were bringing up, well, first of all, remember that if I haven't told you that my spatial reasoning is terrible. So I'm going to have a really hard time reading that and grading that. to be quite honest with you, I might have to break out the kits and be like, does that work? But that means at the same time, it's more ambiguous for the Cambridge graders. So you want to be careful when you are writing out your molecules, how you do your three-dimensional dashes and wedges. I would suggest doing it the standard way. But if you start changing your dashes and wedges, I'm just going to say good luck. All right. So what I was saying is that whatever you have two of, to get the cis version, you need them next to each other. So cis would be next to each other, meaning 90 degrees apart. And then trans means opposite to each other, which means 180 degrees apart. So you may want to write that here, 180, and then cis would be 90 degrees apart from each other. And so what is the ligand I only have two of here? CH3 and H2. So I'm going to go ahead and write from the nitrogen. Which one am I writing here? Is that, am I preparing the cis variant or the trans variant? This is the trans. So this is the trans variant. And then what would I have to fill in the other spots? Water. So H2O, H2O, OH2, and OH2. That's the trans variant. So then how could I convert this to the cis variant? My two groups have to be 90 degrees apart from each other. So if I write my CH3 and H2 or NH2CH3, depending on how you want to write it, at the top, where would I put the other one? Does it have to be here? Where could it be? Where could I put my second one? Any of these four would all be considered correct because they're all 90 degrees apart. Because when you think about it, if you think about the octahedral structure, let's see, probably need more of these little. When you think about the octahedral structure, and that's why I said the kits are helpful here. I don't know. I think at least one of you has a kit at home. You may want to attempt to build some of these to help with your understanding of what's going on. But in the octahedral structure, if I put this at the top, right, this other group is 90 degrees apart. If I turn it like that, it's still 90. If I turn it like that, it's still 90. If I turn it like that, it's still 90. So that's why any four of those spots, like any of the ones that are here, that's all these four that are right here. Does that kind of make sense? So the only trans variant is the one that's 180 degrees apart. And so this one, you choose wherever you want to be. I'm going to choose it to be right here. But I would have to count any of these, correct? Because they are. And so then OH2, H2O, H2O, H2O. And that's it. Which variant is this? They could ask you. This is very. So then, polarity. What's the polarity? Which one's polar? Which one's non-polar?
Trans one is not.
Trans one is still non-polar.
Is it ever going to be polar? The trans one?
I think the trans one is always non-polar, but we'll double check with the opticals. But I'm pretty sure that the trans one is always the non-polar one because the groups are opposite to each other, so they cancel each other out.
Well, wouldn't,
And then this is polar.
wouldn't it be polar because you have on one side the OH together and the other side the H2O together?
No, they're all taken from the oxygen. It's oxygen
Oh, yeah,
and
right,
hydrogen's
yeah.
out. Oxygen and hydrogen's out.
I think it's.
That's why we have to write it. No.
Yeah.
That's why we have to write it that specific way, is to visualize that it's the same. Yes.
And for cis trans, just one pleasure.
Yes.
There can only be two different groups, no? If there's three different groups, where's three?
It would be much more difficult to predict. I'm going to tell you that much. But stick to what the Cambridge standards are, which is with two groups. Well, for octahedral, it's for two groups to predict. Yes.
Will it always be like 2 and 4? Like it's always gonna be like 2 of the other ones.
I cannot guarantee that.
So then how would
There isn't. Keep looking at the homework. State the coordination number of copper in this. What's the coordination number? No.
Oh wait.
What's the coordination number? This is from the last lesson. Well, how many bonds are there? 6. The coordination number is 6. If you know what you're looking at, that hopefully is an easy thing to solve. It's just you count how many bonds there are. All right, next question. This is actually before 2022, but I isolated the question to parts that I think that could still be relevant. Carboplatin and saproplatin are used as anti-cancer drugs instead of cisplatin. Here's these wonderful molecules to look at. Suggests, first question, the geometry of the platinum center in carboplatin. So when they say geometry, what are they looking for an answer? Square planar. So not the bond angle, the actual name of how it's oriented. So it's square planar, that's correct. That's what I said. That question I feel like I could give you. This next question I think is also an important question to look at. This is not exactly the same, but it has the kind of concept that's going on in here. Like this, right? Why can't this carboplatin be cis-trans? Isa.
Because it's bidentate.
Because the one ligand is bidentate and it can only, these two groups can only be 90 degrees apart, not 180 degrees apart. To show that to you, I have a bidentate ligand here. This is the one that I built. The way that it organizes is like this. This is the one ligand going in, the one ligand going in. They're 90 degrees apart. This you can't get to be 180 degrees apart because of the way that it is. That's actually exactly the correct answer. So why does it not show cis-trans isomerism? Since it has a bidentate ligand. The groups could not be, these two oxygens could not be 180 degrees apart. I figured this was a good, like, what would be considered to be a little bit more difficult thinking type question for you to have. All right, so that's cis-trans isomerism. The next topic is optical isomerism. Yes.
Which one's the bidentate ligand?
That's bidentate, isn't it? Because it's the same molecule connecting twice. That can only be 90 degrees apart. It cannot be 180 degrees apart, is the idea. All right, so we are going to move on now to optical isomerism. To help explain this, I think like I told you, my spatial reasoning is not fantastic. That's why I have those built to show you some things. I do have a video of someone explaining it as well. So make sure you're paying as well of attention as you can. These notes will be posted if you need to go back and watch it again, because sometimes you watch something the first time and you're like, oh, what did they say? I know sometimes I'm watching YouTube and I'm like, no, I need to rewatch that one again. So, but pay attention and see what you can gain from this. We are looking at optical isomers. Just to remind you, for optical isomers, in AS chemistry, we were looking for chiral carbons, which meant we had 4 different groups, right? But the whole idea of optical isomerism is that you have 2 mirror images of each other, like your left and your right hand, right? So here, it's not going to be 4 different groups anymore. You're going to see chirality in octahedral complexes. And so for transition metal complexes, you're going to be looking at it with octahedral complexes. So pay attention to the video. And actually, because there's a video, I might get copyright infringement. So let me go ahead. I might have to break this lesson into 2 videos. Remind me to record again, because I'm going to turn the recording off so that